Good morning, everyone. Welcome to Nano Exploration webinar. This is our first webinar of this year, and today it's my great pleasure to host Dr. Zach Hennighausen from our group to present his research. And Zach joined our group in 2023, and he received his PhD in 2019 from Northeastern University, and he also did a postdoc at Naval Research Lab before he comes here. And it is such a wonderful pleasure to work with Zach. He is so energetic and motivated, and his enthusiasm is so contagious. And he's such a great leader and mentor in the group, and also connect us with a lot of collaborators to characterize our materials. I'm so thankful to work with Zach. And yeah, I hope you enjoy his talk today. And before we start Zach's seminar, I would like to mention some housekeeping things. If you have a question during the seminar, please you can write it in the chat, or you can wait until after the seminar, the Q&A time. You can raise your virtual hand, and we can ask the question there. I think with that, I will give the time to Zach. Thank you, Zach.
Awesome. Okay, cool. So I guess people can see me, hopefully see the research. So thank you, Jing, for the introduction. That's very kind. And thank you so much, MIT.nano, for giving me the opportunity to present the work. So this work, it is a conglomeration. It's really a combination of many bushels of people coming together, each solving a unique and complex challenge to make it possible. So this is extraordinary interdisciplinary. I don't know how it would have come together without the help of so many people. So 2D materials, let's dive right in. 2D materials, they are sort of surprising, and they continue to surprise. Actually, for decades, people predicted 2D materials could not exist in the free state. They would need a special environment, but it surprised everyone in 2004 when they started to come on the scene, and they continue to surprise in part because I believe once you stack them, so one 2D material stacked on another, that they will then form new properties. And this formation happens because where the 2D materials overlap, their crystals have an effective multiplication, and they form this moire pattern. You can see this moire pattern. This moire pattern is a new crystal lattice. And as we twist the materials, does it, is it working? Or I don't see the slides moving. Sorry, I was, there we go. Perfect. Now we got it. But as it twists, you can see new moire patterns form. And so new lattices. And this is, how can a lattice make such a difference? Well, think of diamond versus graphite. Both are chemically identical. Both only have carbon, yet they have different lattices and they have dramatically different properties. And the same thing sort of happens with the 2D materials. When we stack them, when we twist them, we can suss out very surprising properties. So I can prime my audience, stacking involves bringing a stamp to the surface, and then when it's released, it can pick a material up, and then you can stack the materials one on each other. Okay, cool. So think that in your mind. So now going on, I'm going to give a quick background of some of my favorite works that show really the impact of this field. So the first one, this is a classic, right? This is a classic, magic angle graphene. Back in 2018, it burst on the scene and everyone was excited. It blew the world away. Actually, you can still find the APS, American Physical Society talk on YouTube by Professor Yario Herrero. And it's like a standing room only, packed room, and they did display other places in the conference room. But it's sort of simple. They took two graphene sheets. I mean, it wasn't simple at the time. It's still not simple, but in conceptually, it's two graphene sheets twisted to a magic angle, roughly, 1.1, and you then can get superconducting activity, and you can even gate it. So you change your carrier density and go from Mott insulator back to superconductor. And this is a stunning result, right? So you can stack these 2D materials, and now you can get superconductivity out. Let's talk about the next one. Ooh, let me start my timer. Jing, I'm just starting my timer, so let me know if I go over. Yeah, 2D magnetics. People also weren't sure if a magnet could exist within 2D materials, but they did find one. It's chromium I3, and at monolayer, it's ferromagnetic. Then if you have bilayer, pristine, so the stacking order is perfect, I believe, then you get antiferromagnetic. But if you twist those two layers, you get domains of ferromagnetic and domains of antiferromagnetic. So we can see as we stack materials, we can get not just different superconductivity, but we can also get unique magnetic behavior. All right, let's move on. Twisted Bisco. So this work is done by Dr. Frank Zhao. He's at MIT, but was previously at Harvard and Professor Philip Kim's group. And they took Bisco, which is a well-known cuprate superconductor, and they twisted it to different angles, 0, 31 degrees, nearly 45 degrees. And they found out at 45 degrees, they got this like really stunning result. They also found they can make a Josephson diode without a magnetic field, pretty stunning. And they got these fractional Shapiro steps. And so this seemingly well understood material, simply twisted, produced a very unexpected or a pretty amazing result. Okay, now we're going to move on. Sliding ferroelectric. So these are quick updates on the amazing stuff that these stacking can do, and it's all sort of in the recent history. Sliding ferroelectrics, you could take certain two-dimensional materials and you stack them in the AA configuration and nothing really happens. But if you go to the AB stack configuration, or the BA, you can get electric fields that form within the material, depending on the direction. And what's neat about this is now let's stack it. Let's put graphene with two HBN sheets, and now we have an HBN as an insulator. Now we can gate it. So we're going to apply voltage. We have electric field going through here. And as you apply an electric field, you switch between BA and AB. And very, very cleverly, this graphene right here acts as a sensor. So we're going to look at some data right here, and you can see the graphene resistance, and you can see two states, two very distinct states. You can almost write one as the on state or off state, so 0 and 1. And they actually then showed it has some major implications for advanced computing. I think it was insanely fast switching speeds, like nanosecond, equipment limitations that allowed them to go to check even faster. And they also like 10 to the 11 or something like that switching cycles, and it still had some pretty good performance. So I encourage everyone to read that paper. It's pretty recent, but it's a stunning finding and very application for industry friendly. Okay, so we just talked about superconductivity, then we talked about magnetism, a Josephson diode without a magnetic field, and then sliding ferroelectrics. And the next stuff, so all the previous stuff was stacked. In this case, so my previous research from Naval Research Laboratory, but I grew bismuth selenide on top of different transition metal dichalconigide monolayers, so TMD monolayers. And bismuth selenide is known for being a topological insulator, and it has these spin protected states. So it, think spintronics and advanced and very, very low power computing. And then the TMDs, they have a strong light matter interaction among many other properties. And so the idea is, can you couple them together? And we found sort of like two exciting results. So this result here is a bound exciton phonon quasi-particle, which are rare quasi-particles. What's unique is it's across the interlayer region. And then on the other side, this work was done at Northeastern when I was a graduate student, but we found indications of a possible purely electronic lattice at the interface. And I believe other 2D materials have also found some indications. So it shows as you combine the materials, in this case, growing them, we can get some unexpected results. Okay, finally, I combined an oxygen transport membrane on top of 2D materials. So oxygen transport membranes, they're very simple. Here's a membrane, you have a mixed gas on one side, and it only allows oxygen to pass through. So the oxygen molecule will break up at the surface, pass through as atoms and then recombine on the other side. And this allows you to make fuel cells. So think clean energy, think hydrogen economy, a lot of promise right there. But in this case, we combined it on 2D materials. And what we can do is we can stuff oxygen into this interlayer region and within the actual oxygen transport membrane, and we can intercalate it and also de-intercalate. And through this process, we can modify the 2D materials properties. So I did it once again with these transition metal like halconides, these TMDs, which have a strong light matter interaction, and I could modify the photoluminescence with high precision. This is using a laser, and we can do it with high spatial precision too. So I tried to write NRL, so go Navy, NRL right there. And how high can we make the precision? So each data point you see in this curve, and there are hundreds, is actually one whole spectrum. We extracted it using fitting. So the error bars are pretty low. So this is the photoluminescence intensity going up in air and oxygen, and then it's going back down in vacuum as we de-intercalate, and it's going back up in air. And you can see we can go up and down by intercalating and de-intercalating, and we can do it with really high precision. So this shows that we have, if you combine oxygen transport membranes, we grew it in this case, but you could stack them. You can then really modify with high precision your 2D materials. So, okay, so we've shown, I believe, some pretty cool stuff right here. We have some superconductivity, magnetism, a Josephson diode, and some ferroelectrics, as well as exciton phonon bound state, pure charge 2D crystal, and also this precision tunability. And so stacking is pretty cool, but there's some issues here. You see, these amazing results over here were done using primary exfoliated materials, which is not super duper industry friendly. They're not they're not crazy about it. And then in this case, I grew bismuth selenide on top, and that was labor intensive, time intensive. So industry likes it. But again, from a research perspective, it's labor and time intensive, and it doesn't work for every material. Maybe I can grow on the TMDs, but can I grow on graphene? Can I grow on hexagonal boron nitride or a random one someone would like to try out? So this begs the question, can we go beyond exfoliate? Can we make these results with non-exfoliated materials? And can we stack nearly any material? Well, let me tell you about a hero of mine, Professor Andrew Mannix, who did have this dream and did try to go beyond. And they made this very novel polymer stamp design. Then they built this exciting machine right here. It's all in vacuum, has a nice turbo pump, and it's all automated. And they were able to pick up and stack MOCVD materials. And what's exciting about that is MOCVD, metal oxide chemical vapor deposition, is very industry friendly. So here you have TSMC saying, well, that's cool. And then they also stacked from the gross substrate, so no prior treatment needed. That's, again, TSMC is saying, well, that's cool. And he also showed it can be done very fast. So 30 layers per hour, which is insane compared to many exfoliated efforts, and stacked 80 layers pretty rapidly, which is also an insane number of layers to stack, right? All monolayer, or near two, but I think monolayer. And so what about the results? Well, this atomic reconstruction of the TMDs, I believe, is an understated result. It's incredible. So you have all these extra spots here. So this is a diffraction pattern. Electrons are diffracting off, but you have all these like tiny little spots, and those are because the electrons are diffracting off of the atoms moving. So his interface cleanliness and quality was so good that the atoms readjust themselves to form these more stable moire patterns, and then the electrons diffract over those new moire patterns. Same wise, the precision of the setup was impressive as well, and you can see through these STEM images, I guess, but cross-sectional, that it's a very clean interface. So 30 layers per hour, 80 layers, very clean. Again, our hero. And so we said, can we do this as well? But can we do it also for more materials? So this is sort of where the talk comes in. We have our setup right here. This is the chamber. We have our camera. We have a pressure gauge. We do things a little different. We put in argon atmosphere, and we don't use a turbo pump. We use a roughing pump, so we only go to like 70 millitorr. But hopefully the argon atmosphere gives a level of cleanliness. We also have two heaters, a stamp heater and a stage heater, so both sides. Um, and let's see what we can, oh, I guess I can tell you a little bit more about the machine. So yeah, so stamp heaters up here. And everything is, for the most part, like home built. Wouldn't have been possible without all the lab mates in my team providing ideas along the way. I could point to any little part of the machine and say, this person helped with this person's idea was this. So very appreciative. And even small conversations in the hallway where someone said, well, you could try heating it. And that was the thing that made it work. You know, it wouldn't have worked otherwise. And so one thing we do is we repeated Professor Mannix's stamp design. We don't have 4 layers, we have 3, but we're working on getting a 4th layer there. And we don't have quite the same, precision and some other stuff, but we are able to stack more material. So we're happy with the progress in that area, but we're working on making a cleaner interface. Cool. So this is the machine we have. Let's see what it can do. Oh, actually, before we tell you about the machine, let me tell you about these shipmates that I work with, this incredible group. So this group I work with, they grow an absolutely insane number of materials in the group. So the group that Jing leads, so we have single crystal graphene. It's grown on these like single crystal copper foils. So the graphene is single crystal for these giant domains. We also make nanoporous graphene, which is very exciting for filtering. Very exciting papers published maybe I think about a year ago. Here are all the various TMDs that are grown within the group. We hexagonal boron nitride, we grow monolayer and very thin, but we also grow thicker, 3 to 20 nanometers. Again, this is all for very large area growth. Carbon nanotubes, ooh, Janus material. This is one of my my faves in the group. So we can take these TMDs and convert this to some Janus. So you make the top layer a different chalconogen atom, and that creates an intrinsic dipole. And these are they have a lot of promise. They have a lot of promise. So cool. So we grow all these interesting materials. And how is the group so productive? Well, one of the group members, Dr. Zhengtao Wang, brilliant researcher, he actually made some software and connected it to some hardware, and things are automated in the lab. So you can see here the fans are starting up, and that's how the furnaces are cooled. But the lids also open themselves and close themselves, and the gas flow rates are also automated. So because the whole process is automated, I believe has led to a significant increase in productivity and efficiency. Also, the growths are, in my opinion, more repeatable. So if I were to start a lab, I'm going to use LabElf. That's what I say. And so cool. Okay, so we have all these different materials. Which materials have we stacked? So up until now, I've been able to stack single crystal graphene, MOSE2, MOS2, WOC2, WS2, niobium diselenide. Actually, technically, I guess it was oxidized at the time. But it used to be niobium diselenide. Hexagonal boron nitride, different layers. MOS2 from the MOCVD front, MOS2 and a Janus variation of MOS2, modular fullerene networks, and exfoliated materials. So far, even though we need to improve our cleanliness, we need to improve our stamps and improve our precision, we are able to pick up these materials, and we're hoping to iron out some of the cleanliness and other things and start churning out results and churning out heterostructures and hopefully collaborate with people who can do some of the characterization. Let me quickly show you guys stamping, what it looks like from the camera viewpoint, and it will make some of the images more clear later. Or the explanations. So here's the stamp, this round thing. We're looking through the stamps. So the stamps are translucent, made out of translucent polymers. And here's some nice gold that's been deposited on an SiO2 surface. And then I treated it to get it to release a little bit. But the gold was generously given by Peter. Sorry, I can't pronounce the last name, but he's in Professor Farnaz Nehru's group. Great person. Encourage you to reach out to him. And so here's the stamp before it makes contact with the surface. Then it makes contact, and you can see that there's a color change. It's due to the thin film effect. So we're in contact, the polymer makes a color change. And then I picked it up, and you can see the gold picked up from the surface. And so that's how the stamping process works. We align things, we make contact, and we pick up, and we see if it picked up. Okay, cool. So I showed you guys earlier, we have this machine. It can pick up the 2D materials. Here's a stamp. It's cut into a square by hand, but it only makes contact where these pillars are that are fabricated using a mold, and I'll explain it all later. And then let me show you. So this is real time, this movie. So here we're going to be picking up different graphene sheets. You'll see it goes into contact. So now it's in contact right there. So it will only pick up graphene right there. Now we just lifted up the graphene, shifting location, and now we're going to go back down and pick up a second layer. And so this is all done real time, and this is the speed at which we can pick up materials. This was a pretty clean pickup, but it could have been better. But if you wait a little bit longer, maybe give it 30 seconds or a minute or 2 minutes, it will become what appears to be a nearly perfect pickup, if not perfect. Cool. And this is where I've tried to do some automation, and it worked out good, but it could be better. And so here we're going to make contact with the surface, and I've automated it by simply telling the motors to go certain distances down and up. This is in contrast to Professor Mannix's research, where there was some optical detection to see when the color change would happen, and then that's when the motor would know when to stop. And so that's what we would like. We would like to go where Professor Mannix did in having an optical detection. It will improve the results, we believe. But we've gotten partial automation so far. Cool. So let's show you a quick snapshot of some of the results. So you can see each of the circles have been picked up. And so it's 10 layers of graphene picked up in 2.5 minutes. This particular graphene was grown on a single crystal copper foil, and the grains are pretty huge. So at least portions of it, I'm sure, were lined up or twisted to the desired twist angle. So hopefully we can repeat some of these incredible twisted graphene results, but use CVD materials and more stacks. The next one is I stacked a multi-layer HBN that we grew from Dr. Kunan Chung, and also some monolayer WS2 and some graphene. And this was just to sort of see how good the interface would look and test it out. And you can see the PL is quenched as predicted, likely due to charge transfer into the graphene. And we see all the various Raman signals from our WS2, our graphene, and our HBN. So cool. So this is just 2 quick snapshots. But I do want to show you a more exciting one that we recently got. So beforehand, we had to cut our 2D material into different shapes. So we use this scratch method right here. And we want to cut into shapes so we could have electrodes be more rectangles, and then we could have squares be where the device would be and stuff like that. And we're trying to reduce the amount of polymer in the process, I guess, for starters. And then 2, we noticed that there was gluing from previous experience when a polymer was used. So we're trying to prevent this gluing so we could pick it up from the substrates. So we have noticed some issues with this tactic, and recently it's not the save all, but it has worked so far for making some devices. And so I'm going to show you guys an MOS2 and Janus heterostructure that we made, so to make a PN junction. And so here's a diagram of our stamp, and the stamp will move to the desired location. We'll go down and we'll pick up. And so here's our first pickup, and we've just picked up a strip of MOCVD MOS2. Now our stamp will move to the Janus side. I'm going to overlap it very carefully, and I will pick up the Janus. That's the second pickup right over here, you can see. And now we're going to do a third pickup. And so you can see how you can quickly move between the materials and deterministically choose where you want to place your 2D material on the stamp, and then pick everything up and then drop things off later. So let's see how things worked out. So here's step 1. Here's our MOS2. I'm looking at the strip. This is what I want to pick up. I made contact. I picked it up, and I don't know if you can see it, but there's a rectangle here. So now I know I picked it up. Unfortunately, my stamp broke, so we still need to make our stamps more reliable, but that's the next step. So we picked up our MOS2, and now I'm going to go over the Janus, and this is me looking over the Janus, me aligning everything, and then I make contact, and I was able to pick it up. And in the end, I was able to stack 3 stacks of MOS2, 3 stacks of MOCVD, Janus, MOSSE, and to the best of my knowledge, picking up Janus materials is very, very challenging, and I don't think very many groups have done this. We might be the first. And so, so this is an exciting heterostructure we made, and I'm working with some students Morgan from Professor Boreskina's group, who's going to be testing some of the PN junction behavior. And I'm hoping to repeat this and make it cleaner. But nonetheless, we're exciting as a first try, and it worked out pretty quickly. One thing I'll note, the Janus materials, they have this intrinsic dipole, and there's a symmetry breaking. So the top layer has been changed, and this symmetry breaking has suggested some really nice properties, some incredible properties. So we're hoping to also do this with single crystals and try them at different twist angles, try optics and devices and gating. Okay, cool. So that's where we are from stacking. We can pick the materials up, but the interface isn't as clean as we would like, but at least we can pick them up. And we can pick up a whole variety of materials. And so now we're looking to characterize. In the meantime, I'm also working on some stamp engineering, not just to improve the stamps, which I believe will decrease the amount of polymer outgassing and improve the interface, but also because we can choose smaller pickup areas, and I believe it can reduce the number of wrinkles probably in the final structure. So I'm going to give you a quick overview how the stamp is created. We have this mold, and it's made using SU8, and then we pour PDMS inside, and then you can pull the PDMS out, and you can functionalize the surface, and you can spin coat a polymer on top, and you bake it, and you repeat it for as many layers as you want. And the top layer is going to be your active layer. That's the sticky layer. That's the one that you want to pick the different things up. And so what we can do is by changing the functionalization, by changing the polymer spin coat speed and changing the ratio of solvent in the polymer, we can make the active area smaller or larger. And you can see it by the rainbows here. So here we have a circle of an inner circle and sort of these like outer rainbows. So two rainbows, double rainbow. And so this inner rainbow, outer rainbow. And the inner rainbow is where the active area is. And you can see from graphene, it only picked up where the graphene was. And this mistake down here, so here's a bad stamp. There's a crack that formed, and when I spin coated my final polymer layer on top, it formed these two bubbles. But it was a blessing in disguise because when we picked it up, we only could pick up where the active layer was, and that sort of hit upon this idea that we could engineer the stamp. This is the team, and they are absolute rock stars. I'm gonna find us growers, problem solvers, and lab mates east of the Mississippi, probably more. And so we're gonna work on cleaning up the interface, making a lot of heterostructures. Folks are helping us characterize them. We can see how far we can push it. I don't know if it's gonna replace exfoliated. Definitely not in the short term, but hopefully it moves the community further along and makes it more industry friendly. And I think I'm looking at the time. I guess like that probably seems good. We have some time for questions. Yeah, any questions, I guess? I hope I didn't go too quick.
Yeah, thank you. Thank you very much, Zach. We have learned so much during the past year through Zach's effort. Now it's question and answers time. You can put your questions in the chat or raise your hand, virtual hand. So now there is a question. Yeah, maybe let me read it. Hi, Zach. Thanks for the great talk. How big is the active area of the stamp? And why did you pick the polymers
Oh, that's
stamp?
such a good question. Such a good question. So the maybe I can show it best with this slide. So okay, so for the active area, okay, so we have this mold, and the mold will determine how big our PDMS pillar is going to be, and that's going to be sort of our max size. But we want to keep making the active area smaller, so we want to make our pillars constantly smaller in diameter. However, as you can imagine, the smaller you make these molds, and then you're asking this gooey polymer to now fill the mold, and eventually you have to pull it out. You literally pull out the PDMS. And this can tear the pillars if the ratio is incorrect, height to width. And the natural thing is, well, why don't you just make the pillars smaller? Well, the smaller you make it, the more it will crash into the surface. So you put your whole PDMS thing on your glass slide, and then it only makes contact where the pillar is. But if this pillar is not tall enough, then you might touch at the edges if you're not 100% flat, which is hard to do. So there's this trade-off where it's challenging to make polymers too skinny. But I think we've gotten it down to 80 microns, but we do as large as 2 millimeters. And we're trying to, depending on the application, maybe someone wants large area transfers and they want many devices in one versus very targeted, where 80 microns might be the diameter here. Also, I think the larger the pillar is, the more reliable the pickup can be, especially in the center region. So at the edges, it sort of can break down and stuff like that. And so I guess to answer your question, 80 microns is so far the skinniest we've tried, but I believe we can get it a little bit skinnier. However, I don't think we get it much based on gut intuition, based on the size of the molds, which is why I believe the active area engineering is promising, because maybe we could engineer something so that the drop of active area is only 5 or 10 microns. And then we're being, yeah, and then we can really, really target things. Okay, and then the type of polymers we chose. Let's see, where do I have my polymer slides? Not here. So actually, maybe I should go to Andrew Mannix's slide. Well, let's do, okay, actually, let's go to Andrew Mannix's slide. It's better. Oops, sorry, right. Here. Okay, so PDMS, because it sticks to glass and you can spin things on. Intermedics has a support layer. We use LOR, liftoff resist 10, I believe, and that was to sort of stabilize the stamp. Smart idea. I think it also allows better spin coating. He also has a release layer where the polymer breaks down when heated. And then there's adhesion layer. The adhesion layer is the really important one. So it uses a polymer called PBZMA. Feel free to email, I can give you the exact stuff, but it's just known for being sort of a sticky polymer, and there's like some arguments that can be made of why it's a good one to pick. But I'm following Professor Mannix's research in this case. But PBZMA is a good choice, and it spin coats. Like you could try using polycarbonate bisphenol A, PC, which is what almost every group uses for exfoliated. However, it doesn't spin coat. It only dissolves in chloroform. It's too volatile. Whereas the PBZMA dissolves in anisole, and so it can spin coat. So the spin coating, which I point out one of the later stuff, is the trick to doing the engineering of the stamps, this spin coating. So you need something that spin coats. Thank you for the question. Very good question.
Yeah, thank you very much. And then the next question is, how do you let go of the monolayer sheet from the stamp? Is it just that when the monolayer is brought close to the substrate, it bonds more strongly to that as compared to the stamp?
Okay, really good question. So I would like to make a stamp similar to Professor Mannix's, where we have this release layer, but I haven't had time to sort of look into that. We've been doing things in piecemeal. However, we have this interim solution, which has worked out actually pretty good. We hydroxylate the SiO2. So shout out to my peeps over in Professor Nurui's group, who really gave me the idea and helped me along with it. But if you hydroxylate the surface, you make the SiO2 very sticky, and then the 2D material just wants to leave, and it sort of pulls off the polymer, and then you rinse the polymer very quickly, and it seems to produce a clean surface, but we have to look into that more. So yeah, so I'm sort of trying to engineer different surfaces. So I drop off currently by functionalizing the SiO2 and making it very sticky, and then it pulls off. And that's reliable, but I don't have to do that, but that's a very, very reliable method.
Oh, yeah, thank you. Thank you very much. And the next question is from Professor Pablo Herrero. Thank you for the nice talk, Zach. Have you characterized by AFM your twisted structures? How uniform is the twist angle?
Oh, such a great, it's an honor, Professor, to have you ask me a question. I remember seeing you down the hallway when you first came to MIT, and I only recognized you from your talks online. So you felt like a rock star. I was like too shy to even say anything. But anyways, that's a very good question. Negative, we have not, but it's like on the work list that we're trying to do. And I know your group is actually, in many ways, leading the efforts to how to characterize these Mori patterns. And so we're actually trying to follow in your group's lead, and I've been reaching out casually to get advice on different stuff. But we definitely want to make a stack and start the characterization to see how even things are. Thank you. Good question.
Yeah, thank you very much. And the next one is thank you so much, Zach, for the fantastic talk. Sorry, I'm not reading everyone's names. I'm sorry. I might have missed it during your talk, but how did you exactly align the MOS2 and the Janus heterostructures? Was it optically?
Yeah, affirmative. Everything is just optically. And so yeah, I literally just sort of like looked over top how it looks. Affirmative. I will say, so shout out to Ed Chen in our group who has made software that can do twist angle detection. So it's all sort of using image recognition to sort of see how much we've twisted the substrate, and that has allowed us to cut down on costs because we don't have to get a calibrated, I guess, rotational stage. But with that in mind, we're hoping in the future to maybe build upon some of that image detection to have it be done more precision. But yeah, good question. Only optically right now and by eye.
Yeah. And then the next one is, hey, Zach, thanks for the talk. How is the sticking working for such a variety of materials? Is it always flat, means parallel to the stem, or is there some tilt?
The only tilt has been accidental, because my problem for a long time was I would crash the sides. And so I've been trying to make things as like non-tilty as possible. And for those who don't know, that's in contrast to exfoliated materials where they do put an intentional tilt, and the idea is to sort of squeeze out and push out junk. And I believe that's one reason exfoliated materials still can produce possibly a better interface, in my opinion. So no, I'm coming down 100% at 0 degree. But the reason it's sticking is, so I've actually left out many details just because of limited talk time and other stuff. And Shiming, shout out to Shiming in our group who's helped me with this. But we sort of like detach the 2D materials. Like they don't want to be on the SiO2 we put them on. And so that allows us to sort of pick them up very easily. And that's how we have such high success rates. We're like making it so they don't want to be on the substrate.
Thank you very much. And the next one, Zach, you are an great expert on this. What advice would you give someone building their own home-built setup in their lab for materials transfer or otherwise? How do you balance cost savings with time and capabilities?
Oh, that is also such a good question. That's such a good question. So I didn't think I could ever build this. And then I got to Professor Kong's group, and people just like believe in things. Like, no, no, we can do it, Zach. No problem. We just sit down and do it. And I was like, okay, I guess we'll try. And I still remember the first meeting we had where people were on a whiteboard and they're figuring out how to build it, and people were being critical of each other, but no one took offense. And it was like a textbook case of how to be a team. And in half an hour, we had charted out a design plan, and it was awful. I didn't go that route, but it was perfect. As we've like iterated on that initial design, it's like slowly moved along. So I think what I've learned from this is I 100% could not have done this by myself. Maybe not even with 5 people, right? Look at the drop off, how I hydroxylate the SiO2. That's Professor Narui's group helping me out. Sarah and Peter and all the different folks there, and I think even in Professor Mannix's group, I visited Stanford. So I went out and visited a bunch of groups. I'm very thankful that people shared their knowledge. And Rita, one of his students, made this like offhand comment, and it's solved our PDMS problem, right? And so I think I just talked to many people. It's 100% teamwork. But I will say the so the motors that I showed you guys earlier that automated, I guess, for our growths. This software that we use for this, we also apply to our machine. So we've had some tremendous cost savings because we make a lot of things ourselves. And I'm thankful for the people in the group for teaching me how to do that. Thank you. It was a really good question. I believe in you. Yeah.
Yeah, thank you. Thank you very much, Zach. And this may have been answered, but maybe you can more specific again. Why is your machine able to pick up more types of material than other designs?
Okay. Really, really, really good question. Okay. It's so I could have done the talk 2 ways. I could have either talked about a machine, or I could have talked about this other work where we're doing, I'm calling it effective exfoliation. But I probably shouldn't say too much. I think we might be able to get a patent from it, and I feel like this talk is recorded. The patent lawyers will find me and say, no, it's already been. But yeah, we have a method for effectively for removing the are these as-grown materials, and we're placing them on SiO2, and they don't want to be on SiO2. In my opinion, that's how I'm looking at it. And so I think there's like different stuff, like when people spin coat PMA and then you fish the PMA out of the water and you put it on top of a substrate, and then you rinse away the PMMA with acetone. I believe there's a gluing aspect going on somewhere there. And I think people will figure it out. Like you have to fish it out of liquid, maybe some residual liquids in between, maybe a 2D layer of water is gluing it or something like that. Um, but there's definitely like an adhesion of sorts. And so we've sort of solved that problem where it's not adhered to the surface as much. And so you can even see some issues with, let's see if yeah. So for example, you see how the graphene's all broken up? That's because this transfer process, which we've improved upon, it didn't work that well. So the graphene picks up from the surface, but it didn't transfer the surface that well because the SiO2 didn't want the graphene. Um, so that's the trick that needs to be figured out. And I can totally, I'm only just, I don't want to rob our group of a patent or another, and so I'm going to avoid saying too much, but please stop on by or send me an email. I can definitely be more than happy to provide more details. But that's sort of the trick. You have to, it's this pre-treatment that makes it not sticky. I'm sorry to be so vague about it, but yeah. But please email me. Thank you for the question. That's a really good question.
Thank you very much, Zach. Hey, Zach, a great presentation. Is the process of finding the 2D material from the substrate automatic or manual?
It's only manual as of right now, but it's one thing we want to automate. And so I think what I've learned from this machine is we have great potential in many directions to go in. So not only can we clean the substrate, but I think we can automate it. So I'm hoping it can be helpful for fundamental science, but then also industry. But if folks are looking to program or help out, we would love the help. And so, yeah, we're working on the programming aspects.
Mm.
Thank you.
And then the next one is what happens to the bonds around the circumference? Is it stamped in vacuum? Could you pass the process in the different gases to affect the resulting electronic properties or symmetry breaking at the edge of the resulting sheets?
I believe so. I was naive. I had the wrong vacuum for a long time, and then we recently changed and made some improvements. Again, under Jing's sort of guidance, and we made these improvements, and I've noticed a big improvement to the stacking process. So I believe the gas that's in there does seem to affect the stack and how much bonding there is and other stuff. But I 100% haven't explored it. I hopefully can get a publication out eventually, and then this will just be like one stepping stone on the way. Very good question.
Thank you very much. And the next one is, hi Zach, super interesting. Do the temperature change when the stamp releases the 2D material compared when picking up?
Oh, such a good question. That is such a good question. Okay, so we found out we effectively had to heat our stamp to get the results to work. And so when we didn't heat the stamp was at room temperature and it touched the heated stage. And what do polymers do when they're heated? They expand. However, the machine was fixed, so the polymer had nowhere to go and it moved and it shifted. And we have tons of movies trying to figure out what's going on and how we can resolve it. And ever since we've added this like heated stamp, it's there seems to be no movement and I don't know, I believe it's a huge increase in performance. And so yeah, so the heated stamp and keeping things the same has improved from that aspect. Did I answer the question actually also?
Yeah, I'm
Okay.
sorry, I just realized that we are running out of time. Yeah, maybe for the other question, we still have a few. You can send email to Zach or ask him in person. Thank you everyone for your great questions and for your interest. The next Nano Exploration seminar will be by also Zach, another Zach, Zhiling Zheng, from um, Department of Chemical Engineering at MIT, and his talk is on atmospheric water harvesting from nanoscale metal organic framework. Yeah, I hope you will enjoy. Yeah, thank you very much.